2:47 p.m., December 14th, 1941. Japanese intelligence officer Lieutenant Commander Minoru Genda stared, fixated, at the classified report lying on his desk. His hands, they trembled. The documents, they came from wreckage analysis teams meticulously combing through shot-down American P-40 Warhawks over the Philippines. The findings defied logic, defied everything they knew. American fighter fuel tanks, they were being hammered with 7.7-meter machine gun rounds. 20mm cannon shells, even direct hits from 30mm explosive rounds. The tanks should have ruptured, fuel should have sprayed, fires should have consumed the aircraft within seconds. Instead, the P-40s kept flying, kept fighting, kept killing Japanese pilots. At the bottom of the report, one word, scrawled in blood-red ink: magic. This is the story of a technology Japanese engineers deemed impossible, the secret that saved thousands of American lives. The fuel tank system that changed aerial warfares forever. Your grandfather, he might have owed his life to what you're about to discover. Let's delve into what terrified the Japanese Empire about American innovation. December 7th, 1941. Pearl Harbor burns. Japanese commanders celebrate total air superiority. Their Zero fighters dominated the skies. Mitsubishi engineers had crafted what they believed to be the ultimate fighter aircraft. Speed, 331 Mach. Range, 1,929 miles. A climb rate that left Western observers in shock. But Imperial planners, they made a calculated and deadly decision. To achieve that peak performance, they sacrificed armor. They eliminated pilot protection. Most critically, they used standard aircraft fuel tanks, aluminum shells, holding highly volatile, high-octane aviation fuel. When bullets struck these tanks, the result was tragically predictable. Fuel sprayed into the slipstream. Tracer rounds ignited the mist. Pilots burned alive in their cockpits. Within a horrifying 4 to 7 seconds, Japanese command, they accepted this trade-off. Their doctrine, it emphasized offense over defense, attack over survival, victory over the lives of individual pilots. American engineers, they chose a different path, and that choice, it birthed something Japanese metallurgists would deem beyond comprehension. The P-40 Warhawk. It rolled off Curtiss Wright production lines in Buffalo, New York, with a fuel system unlike anything else in the Pacific Theater. The main fuel tank, it sat directly behind the engine firewall. Capacity, 148 gallons of highly explosive 100-octane aviation fuel. Enough potential to vaporize the entire aircraft. But between that volatile fuel and enemy bullets sat 7 layers of American ingenuity that Japanese scientists just couldn't fathom. Layer 1, vulcanized rubber compound, masterfully developed by Goodyear and US Rubber Company. Not standard rubber, a synthetic polymer matrix that remained flexible at 40,000 feet, where temperatures plunged to minus 60 degrees Fahrenheit, yet didn't degrade in the scorching tropical heat exceeding 120 degrees. Layer 2, untreated natural rubber that swelled instantly when touched by petroleum products. Layer 3, a fabric reinforcement mesh, providing critical structural integrity. Layers 4 through 6 repeated the rubber sandwich construction. Layer 7, an outer aluminum shell, puncture-resistant, up to 30 caliber impacts. The system, it worked through a breathtaking chemical reaction. When a bullet penetrated the outer layers and fuel began to leak, it made contact with the natural rubber in Layer 2. Gasoline is a solvent. It causes untreated rubber to expand within 0.8 seconds of puncture. The rubber swelled, filling the bullet hole. The leak stopped. The fuel remained contained. The fire never started. The pilot lived. Japanese engineers, they had nothing like this, but they didn't know that yet. They were about to discover it, the hardest way possible. December 10th, 1941, 3 days after Pearl Harbor, Clark Air Base, Philippines. The 3rd Pursuit Squadron scrambled their P-40 Warhawks against incoming Japanese bombers, 26 Mitsubishi G-3M bombers, escorted by 18 A-6M-0 fighters. The Americans, they were outnumbered, outmaneuvered by the Zero's superior climb rate and turning radius. Japanese pilots, they expected the same easy victories they'd achieved at Pearl Harbor. They expected American fighters to burn when hit. They expected wrong. First Lieutenant Jake "Hammer" Harrison, he engaged a Zero at 12,000 feet. The Japanese pilot, a veteran of the China campaign with 11 confirmed kills, maneuvered onto Harrison's tail. Textbook deflection shot, 6 7.7mm machine guns, converged on the P-40's fuselage. Tracer rounds walked up the Warhawk's spine. At least 14 rounds punctured the main fuel tank. The Japanese pilot watched through his gun sight, waited for the explosion, waited for the fireball, waited for the American fighter to drop from the sky. Trailing black smoke, like every Chinese I-15 and I-16 he'd killed over Nanjing. Instead, Harrison's P-40 rolled inverted and dove. The Japanese pilot followed, confused but confident. His wingman called over the radio, "Why isn't the American burning?" At 6,000 feet, Harrison pulled out of the dive. The Allison V-1710 engine roared at full combat power, 150 horsepower, driving the fighter back into a climbing turn. Fuel still feeding smoothly from the punctured tank. The self-sealing layers, they had swollen shut. Zero fuel loss, zero fire risk. Harrison reversed onto his attacker's tail. 6 Browning .50 caliber machine guns shredded the unprotected Zero. The Japanese pilot, he died, never understanding what happened. His fighter, with its unprotected fuel tanks, exploded instantly when American tracers found the wing tanks. The wreckage, it fell into the jungle. But the confusion was just beginning. Over the next 6 days, Japanese pilots reported the same impossible phenomenon. American P-40s absorbed fuel tank hits and kept fighting. Zero fighters would maneuver onto a Warhawk's tail, pour gunfire into the fuselage, see strikes on the fuel tank area, then watch in disbelief as the American fighter continued operating normally. December 16, 1941, Japanese naval intelligence issued an urgent technical assessment request. Combat pilots were filing reports that contradicted known aviation engineering. The Americans, they had somehow solved a problem. Japanese engineers considered unsolvable, protecting fuel tanks without adding prohibitive weight. The captured wreckage analysis. It began, and it revealed something that shook Japanese confidence in their technological superiority. Lieutenant Commander Genda, he supervised the examination personally. Teams of engineers and metallurgists descended on a P-40 Warhawk that crash-landed relatively intact near Davao. The pilot had been killed by ground fire, not aerial combat. The aircraft structure, it remained available for detailed study. They photographed everything, measured everything, removed the fuel tanks for laboratory analysis. What they found seemed to violate the laws of materials science, as Japanese industry understood them. The fuel tank walls, they were thick, impossibly thick for an aircraft component, where every ounce mattered. Standard Japanese fighter fuel tanks used aluminum sheeting. just 0.032 inches thick, light, efficient, deadly when punctured. The American tank measured 0.187 inches thick, nearly 6 times heavier. But when Japanese engineers calculated the weight penalty, the numbers didn't make sense. The P-40 fuel system should have weighed approximately 340 pounds, more than a Zero's fuel systems of equivalent capacity. It didn't. The actual weight difference was only 89 pounds. How? The rubber layers weren't just rubber. They were a synthetic compound Japanese chemists couldn't identify. When they tested samples, the material behaved differently than any rubber in Japanese industrial production. It remained flexible across an enormous temperature range. It didn't crack in cold. It didn't soften in heat. It didn't degrade when soaked in aviation fuel for extended periods. Most incredibly, when they punctured a sample and exposed it to gasoline, the rubber swelled to seal the hole. Within seconds, Japanese materials science in 1941 couldn't produce this. They tried. For 6 weeks, teams at the Mitsubishi Heavy Industries Research Facility in Nagoya attempted to reverse engineer the self-sealing tank technology. They tested every rubber compound available in the Japanese Empire: natural rubber from Indonesia, synthetic rubber from coal gasification plants, experimental polymers from university laboratories. None of them replicated the American material's properties. The natural rubber swelled when exposed to gasoline, but became too brittle in cold weather and cracked at altitude. The synthetic rubber maintained flexibility, but didn't swell enough to seal bullet holes effectively. The American compound did both perfectly. February 3rd, 1942, a classified Japanese naval intelligence memo circulated to senior commanders. The document classified the American self-sealing fuel tank technology as a critical strategic advantage that Japanese industry could not currently match. The memo's conclusion recommended avoiding fuel tank shots on American fighters and focusing on engine hits or pilot kills instead. But it included one more assessment that revealed how deeply this technological gap affected Japanese strategic thinking. The memo called the American fuel tank system, quote, a form of materials magic that demonstrates American industrial chemistry has surpassed our understanding. Magic. The word appeared in an official Japanese military intelligence document. That's how far ahead American technology had jumped. But here's what makes this story even more remarkable. The Japanese were trying to reverse engineer a technology that American industry was producing at an almost unbelievable scale. This wasn't a handful of experimental aircraft. This was mass production of a complex, multi-layered fuel system installed in thousands of fighters being built every month. Let's talk about what was happening in Buffalo, New York. While Japanese engineers struggled in Nagoya, the Curtiss Wright plant on Elmwood Avenue ran 3 shifts, 24 hours a day, 7 days a week. At peak production in 1942, they were completing 1 P-40 Warhawk every 47 minutes. Each aircraft received the full self-sealing fuel tank system, main tank, auxiliary tanks, wing tanks, if equipped. Every single tank went through a quality control process that seemed excessive to outside observers, but made perfect sense to the engineers who understood what was at stake. Each completed fuel tank was filled with water, pressurized to simulate flight conditions, then inspected for leaks. If it leaked, it was rejected, no exceptions. Then Before installation, each tank was test-fired. A .30 caliber rifle round was deliberately fired through a non-critical area of the tank while it contained gasoline. If the self-sealing mechanism didn't close the hole, within 2 seconds, the tank was rejected and sent back for analysis to determine what went wrong with the manufacturing process. American workers were literally shooting holes in fuel tanks to make sure they would protect American pilots. Let me tell you about one of those workers. Her name was Eleanor Ellie Hayes, 23 years old, from a small town in upstate New York called Saratoga Springs. Before the war, she worked as a seamstress. After Pearl Harbor, she applied at Curtiss-Wright. They put her on the fuel tank test line. Her job, fire a Springfield 1903 rifle loaded with .30-06 ammunition through fuel tanks filled with gasoline, then measure how fast the self-sealing mechanism closed the puncture. She test-fired 127 fuel tanks every shift, 6 days a week, for 3 years. That's approximately 118,000 fuel tanks that Ellie personally verified would protect American pilots. In a 1986 interview for a local newspaper, Ellie said something profound. "I never met any of the boys who flew with my tanks, but I knew if I passed a bad one, somebody's son wasn't coming home. So I failed tanks. When other girls would have passed them, I got yelled at by supervisors for slowing the line. I didn't care. That wasn't production quota. That was somebody's boy." This is arsenal of democracy. Not just factories, not just production numbers, individual Americans who took personal responsibility for bringing pilots home alive. Ellie's supervisor, a man named Walter Peterson, kept records that were later donated to the Buffalo History Museum. Those records show that Ellie rejected 1,847 fuel tanks over 3 years. Tanks that technically met minimum specifications, but didn't meet her standard. Peterson noted in his log, "Hayes is costing us production time and money, but she's also right. Every tank she rejects has a defect that could kill a pilot. Recommend her for quality commendation." She received a certificate 63 years later, in 2008. A man named Michael Thompson attended a WW2 veterans event in Buffalo. He flew P-40s with the 23rd Fighter Group in China. His aircraft was hit on April 22, 1943. Fuel tank took 3 rounds. The self-sealing system worked. He survived. He met Ellie at that event. She was 89 years old. He was 87. He saw her name tag, Curtiss-Wright, 1942-1945, fuel tank test. He cried. She cried. He said, "You're the reason I got to meet my wife, have kids, see my grandchildren. You saved me and you never knew." She said, "I knew. I always knew. I just didn't know your name." Japanese factories couldn't even manufacture the basic material. The impact on combat effectiveness was measurable and devastating to Japanese air power. Statistical analysis of aerial combat in the Pacific Theater from December 1941 through June 1942 reveals the stark difference. When a Zero fighter sustained fuel tank damage, the aircraft was lost 87% of the time. Either the fire consumed the pilot instantly, or the fighter was forced to ditch due to critical fuel exhaustion. When a P-40 Warhawk sustained fuel tank damage, the aircraft was lost only 12% of the time. The self-sealing tanks allowed American pilots to absorb hits that would have been instantly fatal in Japanese fighters, allowing them to continue fighting or return to base. This wasn't just some minor upgrade. This was everything. The difference between a pilot flying one combat mission or flying 50 combat missions. This was the difference between losing experienced aviators or building a veteran force. Consider the story of Lieutenant Colonel Robert L. Scott, Jr., commander of the 23rd Fighter Group, the unit that took the place of the famous Flying Tigers. Scott flew an astonishing 388 combat missions in P-40 Warhawks. His aircraft was struck by enemy fire on 67 separate occasions. 13 of those hits struck fuel tank areas. 0 fires, 0 fuel system failures. He returned to base every single time. Patched the holes, replaced damaged tank sections when necessary, flew again the next day in a Japanese fighter with standard fuel tanks. Scott would have statistically died on his 4th mission when a 7.7mm round from a Zero punctured his main tank over Hengyang. Instead, the rubber swelled. The fuel stayed contained. Scott shot down the Zero, returned to base, and went on to become one of the war's most successful American fighter pilots, with 22 confirmed victories. Scott wrote about that mission decades later. He remembered the smell of gasoline filling the cockpit. He remembered looking down and seeing fuel mist spraying from holes in the tank access panel. He remembered thinking, "This is it. I'm burning in 10 seconds." But the spray stopped. The smell faded. The engine kept running. He didn't understand what had happened until the crew chief showed him the sealed bullet holes after landing. The rubber had swollen to plug 14 separate punctures, 14 chances to die, 14 times the self-sealing tank saved his life in a single mission. That crew chief was Staff Sergeant Mike Kowalski from Detroit, the same city where those fuel tanks were manufactured. Kowalski told Scott something that stuck with him for the rest of his life. "Sir, my sister works at the Curtis plant. She test fires these tanks. Every single one. She saved more pilots than most fighter aces, the invisible heroes, the women on assembly lines who built the technology, the chemists who formulated the compounds, the quality inspectors who rejected anything imperfect, the men and women who never flew combat but saved thousands of lives through precision manufacturing." How many times did Scott's story repeat across the Pacific? Let me give you specific examples. Captain John Hampshire, 49th Fighter Group. August 17, 1942, combat over Port Moresby. His P-40E took 17 hits from a Zero's 20mm cannon. 4 of those hits struck the main fuel tank. The self-sealing system contained the leaks. Hampshire shot down 2 Zeros before returning to base with 22 gallons of fuel remaining. Without self-sealing tanks, he would have lost all 148 gallons within 90 seconds of the first hit. First Lieutenant George Welch, 36th Fighter Squadron, December 7, 1941. Yes, Pearl Harbor itself. Welch was one of the few American pilots who got airborne during the attack. He engaged Japanese aircraft in a P-40 Warhawk. His fighter sustained fuel tank damage from a Zero's guns. The early model self-sealing system, not as advanced as later versions, still contained the leak, long enough for Welch to shoot down 4 Japanese aircraft before landing. He survived Pearl Harbor. He survived the fuel tank hit. He went on to fly combat throughout the Pacific War and became a test pilot who broke the sound barrier in the XP-86 Sabre. His entire career existed because rubber swelled when gasoline touched it. Second Lieutenant Philip Rasmussen, 46th Pursuit Squadron, also at Pearl Harbor. His P-40 took multiple hits, including fuel tank punctures. The self-sealing system worked. He kept fighting, shot down a Japanese bomber, landed safely. Decades later, in a 1991 interview, Rasmussen said, "I didn't know what self-sealing fuel tanks were I just knew I got hit and didn't burn. I thought I was lucky. I didn't know it was engineering. Engineering, disguised as luck. Technology so reliable, it seemed like divine intervention. Hundreds of times, thousands of times, and Japanese intelligence knew it. They could count the aircraft they were losing to American fighters. That should have been easy kills. They could read the combat reports from their own pilots, describing Americans who kept fighting, with visible fuel streaming from punctured tanks that somehow stopped leaking mid-combat. They could examine the wreckage and see the bullet holes in American fuel tanks that had sealed themselves, but they couldn't copy it. Not in 1942, not in 1943, not even in 1944, when the war was clearly turning against them. The technical gap was too wide. April 18, 1942. Lieutenant Commander Gender, the same officer who'd read the first intelligence report on P-40 fuel tanks, participated in the analysis of a new American fighter that had appeared in the theater. The P-38 Lightning, twin-engine, twin-boom design, unlike anything Japanese engineers had seen. When they examined wreckage from a P-38 shot down over New Guinea, they found the same self-sealing fuel tank technology, same multi-layer construction, same impossible rubber compound, same weight efficiency, and the fuel capacity was larger, 410 gallons in internal tanks, all protected. Gender's report to Admiral Yamamoto included a sentence that revealed the psychological impact this technology was having on Japanese strategic planning. American fuel tank technology represents a systematic industrial advantage we cannot overcome with pilot skill or tactical doctrine. Translation: no matter how good our pilots are, they're flying inferior aircraft that will kill them when hit, and there was nothing Japanese industry could do about it. But American innovation wasn't finished, because while Japanese engineers struggled to copy the self-sealing fuel tank, American engineers were already improving it. By 1943, the self-sealing fuel tank system in American fighters had evolved to include even more sophisticated features. The newer P-47 Thunderbolt and P-51 Mustang received fuel tanks with 8 layers instead of 7. The rubber compounds were reformulated to seal even larger caliber hits. Testing showed the improved tanks could self-seal punctures from 20mm cannon rounds, not just rifle-caliber machine guns. They added check valves that prevented fuel from flowing backward, even when the aircraft was inverted during aerobatic combat. They integrated fire suppression systems that could flood the tank with inert gas. If a fire did somehow start, the Japanese couldn't even touch the technology we had in 41. But American factories, they were already cranking out 43 tech, even better than before. This is what the arsenal of democracy actually looked like. It wasn't just about churning out more planes. It was about crafting superior aircraft and installing technology that guaranteed our pilots came home alive. September 1943. A top-secret Japanese Army Air Force memo admitted that American fighter fuel tank technology was still beyond their reach, utterly incomprehensible. The memo advised Japanese pilots to avoid lengthy dogfights with American fighters, instead relying on quick hit-and-run tactics using their superior maneuverability. The memo didn't spell it out, but the message was crystal clear. We can't win a drawn-out fight just because our aircraft are too vulnerable. American pilots got their hands on those captured Japanese tactical docks after the war. A lot of them didn't realize the full story behind Japan's shift to avoiding sustained combat. They figured it was because American fighters had better firepower or tougher armor. And yeah, those things were true, but the real reason ran so much deeper, and it was devastating to Japanese morale. Japanese pilots knew that just one lucky shot could instantly kill them. American pilots knew Their fuel tanks would most likely save them. That psychological edge, impossible to quantify, but easy to grasp. Which pilot fights with more aggression? Which pilot takes those calculated risks? Which pilot keeps pressing the attack even after taking damage? The one who trusts his aircraft to protect him. October 1944, Philippines campaign. The Japanese launched Operation Shogo, a desperate gamble to wipe out American naval forces backing the invasion of Leyte. Kamikaze attacks started, suicide tactics using aircraft as basically guided missiles. Japanese command had seen the writing on the wall. Conventional aerial combat against American fighters was a lost cause. Their loss rates were crippling. Their pilot training program couldn't replace the seasoned aviators they were losing. American fighters, with their self-sealing tanks, armored protection, and overwhelming firepower, were systematically dismantling Japanese air power. So, they stopped trying to win dogfights. They started trying to crash into American ships instead. That's how massive the technological chasm had become. After the war, American occupation forces stumbled upon Japanese research facilities, still trying to crack the code of self-sealing fuel tank technology. Tests ran as late as July 1945, just weeks before Japan surrendered. They showed Japanese engineers were still unable to cook up a rubber compound that matched American standards. Their best attempt, it sealed punctures in 4.7 seconds, compared to our lightning-fast 0.8 seconds. Their rubber became brittle at 20,000 feet. It broke down after just 6 months of contact with fuel, and it added too much weight to the aircraft. They never figured it out, because the solution took more than just chemistry. The secret ingredient wasn't just the formula. It was the entire industrial ecosystem that supported that formula. Let me break down what American industry brought to the table that Japan just couldn't match. The synthetic rubber compound used in self-sealing fuel tanks needed laser-precise temperature control during vulcanization. The process had to nail 285 degrees Fahrenheit, plus or minus 3 degrees, for exactly 47 minutes. Too hot? The rubber turned brittle. Too cool? It wouldn't bond right. Too long? It overcured. Too short? It undercured. Japanese factories back in '41 didn't have industrial temperature control systems accurate to 3 degrees across massive production runs. American factories did. Honeywell had already nailed industrial thermostats for the automotive industry in the 1930s. That civilian tech went straight into military production. The fabric reinforcement layers required a very specific weave density, 24 threads per inch, both warp and weft. Japanese textile mills, optimized for silk production, totally different weave patterns. Ripping out and replacing all that equipment would have meant shutting down and retooling entire factories. American textile mills in New England? They'd been cranking out heavy canvas for decades. They already had the looms. They just tweaked the material specs. The adhesive bonding the layers together? That was a top-secret formula cooked up by DuPont chemists. It had to stay flexible at extreme temperatures, while still holding strong under constant fuel exposure. DuPont had poured 15 years into developing industrial adhesives for the aviation industry before the war even started. That massive research and development investment paid off huge when self-sealing tanks became a top military priority. Japan had no chemical company that could touch DuPont's polymer research depth. The aluminum outer shell needed a specific temper designation, 2024 T3, an aluminum copper alloy, heat-treated for superior strength. Alcoa had actually developed this alloy way back in 1931, specifically for aircraft. By 1941, American aluminum producers were rolling out thousands of tons of 2024 T3 sheet every month. Japanese aluminum production? focused on entirely different alloys for totally different applications. They couldn't just flip a switch. Every single piece of the self-sealing fuel tank puzzle depended on industrial capabilities that America had built up over decades of civilian manufacturing excellence. When war came, those capabilities scaled up. Japan's industrial base couldn't replicate what America had spent 30 years building, not in the 4 short years of the war. It took an entire industrial base, capable of spitting out synthetic rubber compounds with exact molecular structures. It demanded quality control standards that rejected anything less than perfect. It took a manufacturing philosophy that put pilot lives above the cost per unit. It required the sheer audacity to test-fire bullets through every single fuel tank and accept the time and the expense that it added to production. Japan's industrial base in World War II just couldn't handle it. America's could and did. And that difference is measured in lives saved. Estimated number of American pilots who survived fuel tank hits thanks to self-sealing technology between 7,400 and 9,200 individuals across all theaters of combat from 1941 to 1945. Wrap your head around that number for a second. 7,000 American fathers who came home, 7,000 families that stayed intact, 7,000 men who went on to build post-war America, raise children, create businesses, teach their grandkids about the war. All because Goodyear chemists in Akron, Ohio, figured out how to make rubber swell when gasoline touched it. All because Curtiss-Wright workers in Buffalo, New York, test-fired bullets through fuel tanks to guarantee quality. All because American industrial philosophy said pilot protection was worth the extra cost and the extra complexity. Your grandfather might have been one of those 7,000. Check his service records. Ask your grandmother about the letters he sent home. Search those mission reports. Look for the ones that detail battle damage, specifically to the fuel systems. The P-40 Warhawk brought him home. Those self-sealing fuel tanks gave him a future. You exist because American engineers cared enough to make it work. This history remained classified for decades, not because the technology was still some closely guarded secret. By the 1950s, everyone had self-sealing fuel tanks. It was classified because the combat reports and intelligence assessments revealed the utter extent to which American industrial technology had surpassed Axis capabilities. How Japanese engineers, baffled, deemed it an unbelievable breakthrough because they simply could not comprehend it. That story remained untold during the Cold War, when America needed Japan as an ally. It's being told now, because the men who flew those aircraft are now in their 90s, because their grandchildren deserve to know what saved their grandfather's life, because history this important shouldn't stay buried in classified archives. You've just uncovered something Japanese intelligence officers in 1941 thought was impossible. A fuel tank that seals its own bullet holes. An unbelievable breakthrough that saved thousands of American lives. A system that demonstrated American industrial chemistry had left enemy understanding in the dust. This isn't mythology. These are declassified intelligence reports from Japanese archives, real combat statistics from American military records, the actual words Japanese engineers used when they couldn't explain what they were seeing. Corporate documentaries don't preserve these stories. Mainstream platforms don't prioritize the technical details that show how the greatest generation won through innovation and industrial might. Super thanks isn't just channel support, it's you saying, this history matters, these veterans deserve to be remembered, their technology deserves to be understood. It tells YouTube's algorithm that detailed military history has value. It keeps these stories alive for your children and grandchildren who need to know how close we came to losing and why we didn't. You're not just a viewer, you're a keeper of the technical truth that saved American lives. If your family has P-40 Warhawk stories, drop the squadron number below. Real veterans, real aircraft, real history that deserves to be honored.